The difference between this example and the last example is in the last one they actually gave us an x value that we were finding the slope of the tangent line at. On this problem we're asked to do it arbitrarily, so what we're going to end up with is a whole nother function, okay? Because what's going to happen is the following. So let me draw a picture of what's going on. If I take this x to the third as a function here, okay, it's going to look something like this. That's the cube function. Now, if I go ahead and if I look at a tangent line somewhere, let's say I look at a tangent line here, okay, it'll look something like this, okay? But if I look at a tangent line, maybe let's say over here, it'll look maybe something like this. Or if I grab a tangent line maybe here, it'll look something like this. Do you see how, or even down here, it'll look something like this. Each of these white lines is likely to have a different slope, okay? And that's the derivative. The derivative is the slope of the tangent line. Now, since each one of these has a different slope, we're going to, when we do the differentiation of x to the third, we're going to find a function that's going to allow us to plug in the x value. Like, for example, here's x. If I plug in 2, okay, and this guy's at 2, it'll tell me the slope at 2. If I plug in 1 and this guy's at 1, it'll tell me this slope. If I plug in -1 into the function, it'll tell me this slope. And if I plug in -2, it will tell me this slope right here. So we need a whole other function that when I plug in the x value, it's going to show me the slope. So here's how we're going to do that. Let me erase this picture. It's always good, like I said, draw out a picture so you can see what's going on. I'm going to take the cube function again. Again, it looks something like that. And I'm going to pick an arbitrary point on it. It really doesn't matter where you pick. So let's say I pick an arbitrary point right here. Let's just call it x. And now, so when I say I'm picking x, I mean that's the x value for that arbitrary point. They're actual points, not x. Okay, hang on one second. And now what we need is we need the height of this guy. And so the height, remember this is f of x, which is equal to the cube function, so its height is x cubed. Okay. Now we're going to go a little bit over. I don't know how far. We're just going to call this distance. This distance that I go over, we're just going to call it delta x, which means that if this was x, then this has got to be x plus that distance that we went over. Like if this was 2 and the distance we went over was 3, then this is going to be a 2 plus 3, which would be 5. Now we'll go up to the function. This is exaggerated, of course. And we'll go over, and this guy is at a height of x plus delta x. Oh, I ran out of room. Let's pull this back just a little bit. X plus delta x cubed. That's this height right here. Now this is f at x. This guy is f, whoops, it doesn't write real well on the side here, so I'll just write it right below. F at x plus delta x is equal to that guy. Okay, so the difference quotient says, and that's the difference quotient says, look, if I want to find the slope of this line, what I'm going to do is I'm going to take these 2 points and I'm going to push this point really close to this point by letting delta x become super small, because that takes this point, moves it towards this point, which moves this down like that. Okay, so how are we going to do that? Well, we're going to take the limit as delta x goes to 0 now of our difference quotient. So I need this yellow distance. Our yellow distance is f at x plus delta x minus f of x over this green distance, which is just delta x. This is your difference quotient right here. We're going to take the limit of this. So the limit as delta x goes to 0, f at x plus delta x, we already have it, it's right here. So that is x plus delta x cubed. F at x is this guy right here, which is x cubed, all over delta x. Changing your y value, that's this yellow. Changing your x value, that's this green. And so that's the slope. That is the slope of this line. I'll dot it in here, right here. As I take the limit as x goes to 0, I get the slope of this solid white line right here. That's the idea. So let's keep working this guy out. This is going to give me the limit. Actually, I'm going to need some space here, so I'm just going to draw a line over here, and we'll work that guy out. So that's the limit as delta x goes to 0 of the following. So I'm going to have to go ahead and cube this guy. My recommendation is you use Pascal's triangle and the binomial theorem. So if you don't know that, if your pre-calc instructor didn't talk to you about the binomial theorem, you want to go ahead and get a YouTube video on it. So I'll write it out here as the binomial theorem, and you can use, whoops, that's a 1. You can use your coefficients. You can get them from Pascal's triangle. Okay, so I'll write that down below here. Pascal's triangle. Okay, and so I'm cubed, so I'm using this guy right here. So when I multiply this thing out, it's going to be x to the third plus 3x squared delta x plus 3x delta x squared plus delta x cubed. Okay, that right there is this guy right here multiplied out. And then, so of course we still have to subtract x cubed, and we're going to divide that by delta x. Again, if you don't know the binomial theorem and how I did this out, you probably want to go watch a video on it. I would just go to YouTube and just type that into your search bar. So this will be the limit as delta x goes to 0. By the way, if you do know it, then you should go back and thank your pre-calculus teacher. Okay, so go, buy them a coffee, or just say thanks. They'd really appreciate it. Anyway, so let's get rid of these. These guys cancel out, and I'm left with the following: 3x squared delta x plus 3x delta x squared plus delta x cubed. Now, I don't usually put this guy in parentheses, but you can because it's one item divided by delta x. Now I'm going to factor it out. Oops, that's not supposed to be a delta, that's supposed to be an x. Okay, and then this is going to be the limit as delta x goes to 0. These guys now can cancel out, and I'm left with 3x squared plus 3x delta x plus delta x squared. And as delta x goes to 0, this guy goes to 0 and this guy goes to 0, meaning these terms, they drop out. And so all we're left with is 3x squared. Now you remember, I said to you way back at the beginning that because the tangent line changes, the slope of the tangent line changes all over the place here, we're going to end up with a function here. So watch what's cool about this 3x squared. If you went over, let's say x was 2. If you went over to 2, then the slope, if this was 2 over, then the slope of this line right here would be given by taking 2 and plug it into there. So it would be 3 times 2 squared, which is 3 times 4, or 12. So when we go 2 over, the slope of the tangent line on the cube function, the slope is 12. Let's say we went over 3. So let's say we had the cube function, and we went over 3, and then we went up, and we wanted the slope of that line. Well, then it's going to be 3 times 3 squared, which is 27. Okay, so what the cool thing about this, doing it in general, is we come up with a function that allows us to find the slope anywhere. Unlike the last problem where we only found the slope at one specific point, this guy lets us find it everywhere. And this, by the way, 3x squared is what we call a derivative. And the notation that we use for that, let me get rid of this for a second. The notation that we use for that is f prime of x is equal to 3x squared. Or we use the notation dy dx is equal to 3x squared. This is the Leibniz notation, and I always forget if there's supposed to be an I before the E. No, it's EI. So the Leibniz notation is this, and it means the same thing as this f prime. And f prime just means the slope of the tangent line at this given x value. Don't worry, we'll try more problems.